Good day, everyone. Today we're going to start talking about the information in Chapter 18. And Chapter 18 is titled Phases in Energy. And so in this chapter, we're going to look at the different phases of matter and energy. And so section 18.1 starts out by discussing the three phases of matter that exist on planet Earth, and those phases being your solid, your liquid, and your gas. Now, what you need to remember, majorly important topics about these different phases is you need to remember how these particles are organized in these three different phases. Please remember when you're dealing with solids, solids are well organized. And even though the temperature is low, the particles are still moving. They're vibrating in their position. Okay, they're held in rigid fixed positions, but they're still moving. When we move to liquids, though, we notice that the organization gets a little less orderly, and that liquids generally take up a little less space than solids do because, again, they're not organized as orderly as your solids are. But there still is an attraction between the particles, which is what holds liquids together. And so in your solid phase and in your liquid phase, there's very little space between your particles. But when you go to your gaseous phase or your vapor phase, then that's where you see that those particles are allowed to move freely to wherever they want to go. And so when we have gases, they will always spread out to fill up our whole container. There's a lot of empty space between the particles and gases because, again, there are no forces of attraction there that are holding those particles together so they can go wherever they want. And wherever they want is restricted by the size of whatever their container is. Now, one of the things that you're going to talk about in this chapter is how do you move between these different phases. So you can see behind me. Our three different phases are our solid, our liquid, and our gas. Notice when we want to go from a liquid to a solid, we call that process melting. Your book also refers to that process as fusion or fusing. When we go from a solid to a liquid, that I'm sorry, I said it wrong. When we go from a liquid to a solid, that process is called freezing, and freezing is also known in your book as solidifying. Okay, when we go from a solid to a liquid, that's our process that's known as melting. And again, in your book, it's referred to as fusion, and you'll see why that is in just a little bit. When we go from liquids to gases, most people are familiar with that process. That process is known as vaporization, not evaporation. There is a difference between vaporization and evaporation. So please make sure you remember that that process going from liquid to gas is known as vaporization. When you go from gas to liquid, that process is known as condensation. And most of us are familiar with that from the water cycle. Now, the two processes that students have the most trouble remembering is our going from solid to gas or gas to solid. And these processes occur without the appearance of a liquid. So a lot of times we have difficulty understanding these because we don't encounter a lot of compounds that do this. But if I'm going from a solid to the gas phase, going from a solid to the gas phase, that's known as sublimation. And if I'm going from the gas phase to the solid phase, that's known as deposition. Now, examples of where you can see sublimation, if you buy those air fresheners like you buy from Dollar Tree, and they are solid and you pull the top on them to expose the solid, well, you'll notice that you smell the gas after you pull that top up. And that's because that solid has become a gas. Another example of sublimation occurs when you're dealing with mothballs. If you put out mothballs, you'll notice that mothballs are solid, but shortly after you put out those mothballs, if you go back and look at them, you don't see a puddle of liquid. You still see the solid there, but you can smell the smell that comes from mothballs. So those are a couple of examples of sublimation. Now, when we look at deposition, if you think about what happens when it's cold outside, where you've got the water vapor, and again, vapor is a form of gas. You've got water vapor that's in the air, and when you step outside, the grass kind of crunches under your feet because frost is a situation where you get deposition, where that gas has become a solid. Another place that you can see deposition happening is in your freezer. That's why you get that ring of ice around your freezer that has to be defrosted, is because of the air that's in your freezer actually has water in it, and that gas, that water vapor, deposits on the sides of your freezer or your deep freezer, which is why you have to defrost those things. So those are some major points that are made in that very first section. Your book also refers to terms like your melting point, which it defines the melting point as the temperature at which a pure substance melts, and your freezing point, and that's the temperature at which a pure substance freezes. And what you need to understand is that melting point and freezing point, they are the same temperature. Because those processes go in reverse. Whether I say melting point or whether I say freezing point, we're talking about the same temperature. So please don't get that confused. And normally when we say melting point, we're talking about at the normal or standard atmospheric pressure, which we usually signify as 1 atm. Now, when we deal with our vapor pressure and our boiling points, what you need to know is that when we talk about vapor pressure, we're talking about how the pressure that's exerted when I have a liquid and the gas particles that are above that liquid, that pressure that those gas particles exert on the liquid is known as your vapor pressure. Your book mentions that liquids boil when your vapor pressure is equal to the atmospheric pressure above it. And so you need to be familiar with that. When we talk about boiling points, remember, we're talking about boiling point, the temperature at which a liquid becomes a gas. And remember, those boiling points differ based upon the material that you're looking at. And again, boiling points are kind of standardized. We're talking about a pressure of 1 atmosphere. And so we can identify substances based off of what their boiling points are, because boiling points are specific for materials. Now, in section 18.2, that's where we start talking about energy, specifically potential and kinetic energy. Your book starts out by mentioning the law of conservation of energy, which says that energy is neither created nor destroyed. It can only change form. And so when we define kinetic energy and potential energy, we define kinetic energy as our energy of moving, or our motion energy related to motion. When we define potential energy, we're talking about energy that is stored or is related to position. Now, your book does give you the formula to find kinetic energy. That formula is given as kinetic energy equals half the mass times the velocity squared. So when you're looking at kinetic energy, how fast the material is going is more important than the mass. So that's why on the highway, if you're going really, really fast, that will increase your kinetic energy versus having an object that is going very slowly. Now, when you do consider mass, mass does play a part in kinetic energy. It's just not as big a part as velocity is, because you'll notice in the equation, velocity is squared. So that's why if you see like a transfer truck coming towards you on the highway, you should never pull out in front of that transfer truck, because again, that transfer truck, because of its mass and because of its speed, is going to have a much higher kinetic energy than you would pulling out in your vehicle. Okay. And so when we think about temperature, temperature is actually a form of kinetic energy. It's a measure of the average kinetic energy of the particles in a substance. And so when your temperature increases, what we find is that the particles in the substance move faster. All right. When we look at potential energy, on the other hand, again, potential energy is stored energy that is related to position. And so you can see in the diagram that I have here, if I've got a person who's standing on the edge of a cliff, they have a much higher potential energy than somebody who's standing on the ground would have. And the reason they have that higher potential energy is because they're further off the ground. So the further away from the ground you are, the higher your potential energy. All right. Your book then moves into talking about phases and temperature. And so when you look at phases and temperature, it a lot of times helps to have a phase diagram. And so I've drawn an example of a phase diagram here. And please notice that we've got pressure and temperature. And notice in our phase diagram, there are 3 specific regions. Notice the one at lower temperature and lower pressure is going to be your solids. You've got the liquids beside that in blue, and then you've got your gases underneath that. Now, what you need to understand is that at a phase change, and all of these black lines that are on the graph, not the actual graph itself, but all of these black lines that are between the solid phase and the liquid phase, the solid phase and the gas phase, the liquid phase and the gas phase, those actually represent your phase changes. And so at those phase changes, your material will be present, but you'll have particles that are in both phases. So when you're on that line, you've got materials that are present in both the solid phase and the gas phase. And so if you have those, then you're at a phase change. Your book then goes on to look at phase changes and energy. And so for this particular topic, it's usually easier to look at a phase diagram in a different fashion. And so if we look at this phase diagram, you'll notice now that we're proceeding in time for our reaction. Temperature is on our vertical axis. And you'll notice that we've got 3 regions where we're rising, and then there are 2 regions where there are plateaus. And so what you need to understand is that anytime you get to an area where you're changing phase, you have to put in energy so that that material can break the bonds of attraction that are between the materials. And so that's why we've got these plateau places. Again, those places indicate where bonds are being broken so that I can go from one state to another state. Now, please also notice that there are 2 plateaus, one between solid and liquid and one between liquid and gas. What that means is at phase changes, the temperature does not change. So if we're talking about water at 0 degrees Celsius, that's where solid water becomes liquid water. After 0 degrees Celsius, your liquid water can change temperature, but At that position where you're changing from solid to liquid, there is no change in the temperature. And the same is true of the boiling point of water. We know that water boils at 100 degrees Celsius. So at 100 degrees Celsius, that water is going from the liquid phase to the solid or to the gaseous phase. And that energy that's being pumped in is being used to break the bonds of attraction that are between the liquid molecules. And so you'll notice that the line between solid and liquid is shorter than the line between liquid and gas. And that's because it takes a lot more energy to make a liquid become a gas than it does to make a solid become a liquid. And we'll spend some time talking about that in just a moment. But please remember, when we're looking at potential energy, your potential energy for your solid is less than the potential energy for your liquid, which is obviously less than the potential energy for your gases. So gases have a much higher potential energy than do liquids or solids. And that should make sense for you. And your book gives you some practice with some problems like this before in section 18.4. It moves on to talk about specific heat capacity. And it introduces terms related to energy and heat in particular. One of the terms that it introduces is the unit joule. And please remember that the joule is the SI unit of energy. And we will be using that to measure our energy in this course. We also use the units calories to measure energy, and we abbreviate that as lowercase CAL. Now, when we're talking about calories, that term should be a little familiar to you. You've encountered the word calories when you think about your food consumption, but please remember there's a difference between chemical calories and nutritional or food calories. When you're dealing with food calories are generally abbreviated with a capital CAL, letting you know that we're talking about food, and the energy calories or chemical calories are lowercase CAL. And now the difference is that one food calorie actually equals 1,000 chemical calories. And you need to be familiar with that term. Now, you also need to know that one chemical calorie is equal to 4.184 joules. And so that's a conversion that you will need to use. You can use that as a conversion factor. Again, that conversion factor is that one chemical calorie equals 4.184 joules. That's a conversion factor that you need to commit to memory, because you will be using that as we move into the next section, which is on specific heat. And we'll talk a little bit more about that in just a moment. All right, so if we consider our specific heat formula as represented in your book is Q equals C times M times delta T, where Q stands for your heat, which is either measured in joules or calories. If it's not in joules or calories, you have to convert it to get it to be in joules or calories. On some of your problems, they may give it to you in kilocalories or kilojoules. Please remember, you will have to do a conversion on that if that's not what you're looking for. C represents your specific heat, and depending on what your specific heat is measuring, that specific heat does vary as you change from material to material. So even like solid water versus liquid water, those two materials have two different specific heats. And so the units that are generally given are joules per gram times degrees Celsius, but it could also be given in calories per gram times degrees Celsius. Your M stands for your mass, which is given in grams. And again, if it's not given in grams, you have to do a conversion to get it to the right units before you plug it into the equation. And your delta T, that delta actually stands for the change in, the T stands for temperature. And so the units for your temperature should be in degrees Celsius. Now, how do you find delta T? You do it by taking the final temperature and subtracting out the initial temperature. That will give you your change in temperature that you need for your formula. Now, please make sure that you understand that there is a difference between heat and temperature. Heat we can calculate. Temperature is actually a measure of the kinetic energy, and so you need to be familiar with that. Then your book goes into talking about units and signs. So make sure you read over that information there. And then in section 18.5, it goes through some heat calculations. And so if you are doing a problem where your material all stays the same state of matter, then you can use the specific heat formula. If you're doing a problem where your material all stays the same state of matter, so like we know that water is frozen at 0 degrees Celsius, and we know that it boils or becomes a gas at 100 degrees Celsius. So if I'm talking about water and I want to measure the energy, then if I have water that's at like 25 degrees Celsius and it's going to 75 degrees Celsius, then I can use the specific heat formula. However, anytime your material goes through a phase change, the specific heat formula would no longer work. Okay, and so if you're doing a problem where you've got to change state, you need what is talked about in section 18.6 and 18.5, where you start talking about your specific heat capacities at your different temperatures, your heat of fusion, your heat of vaporization. You need those values when you're looking at a phase change. So like if they gave you ice that was at -5 degrees Celsius and you were going to liquid water at 20 degrees Celsius, you would actually have to do 3 problems. You have to do one problem where you go from ice at -5 to ice at 0. Then you have to do a problem where you consider the phase change, how much energy is required for that phase change from solid water at 0 to liquid water at 0. And then you would have to do another problem where you go from liquid water at 0 to liquid water at 20 degrees Celsius or whatever that final temperature was. And then to find the total amount of heat, you would just add those 3 heats together to find the total amount of heat. So your book gives you several examples of going through problems where you're using equations and doing heat calculations. Biggest thing is you've got to make sure that your units match up with what you're given in the problem. So if they give you a mass and it's not in grams, again, remember you've got to convert it to grams. If they give you a temperature and it's in degrees Fahrenheit, remember you've got to convert it to degrees Celsius. Just please make sure that you set up your problem so that those units can cancel out properly. Now, I hope that this helps with this chapter. You'll find your review quiz beginning on page 368, going to 369, and then you'll find the answers for that review quiz on page 372. If there's anything I can do to help you as you go through this material, please reach out and let me know. I hope you all have a good rest of your day. Thank you so much. I hope you enjoy.